In this video, we are going to discuss about a very important part of the chapter combinatorics, which is called derangement problem. Derangement problems. Now, what exactly derangement problem deals with? It is basically permutation of objects in such a way that no objects are placed in its right place. This kind of problems are what called your derangement problems. Let us take an example that there are n letters. Let us say the letters be L1, L2, L3 and so on, Ln. And we are having in self-addressed envelopes E1, E2, E3, En. L1 is the envelope where the address of the letter E1 is written. L2 is the letter whose corresponding envelope is E2, and this way. Now, derangement means, as I told you, you have to place or you have to arrange all those n letters in these n envelopes in such a way that no letter is placed in its right envelope. How to do this sum? Well, I will try to do this problem by two methods. The first one, I will use principle of inclusion and exclusion, which is also popularly known as pi method. And the second method will be recurrence relation. Okay? So let us start with the first method, and then I will teach you how we can find out the total number of derangement by using recurrence relation, right? So first way we will do, which is actually we will be using principle of inclusion and exclusion. Well, our main goal is, what is our goal? Our goal is that you have to place, you have to arrange those n letters in n given envelopes such that no letter is placed in its right envelope. That actually what derangement is all about. So how to do that? Let us say I am doing by the first method, which is our principle of inclusion and exclusion. Let me just denote AI. What is AI? It is basically the ith letter when placed in its right envelope. that is in the envelope EI. So what do you mean by A1? A1 is the letter L1 is placed in the envelope E1. What is A5? The fifth letter, that is L5, is placed in its right envelope, which is E5. Now, what do you want? I want that the first letter should not be in its right envelope, that is A1 bar. And the second letter will be also not in the right envelope, so it is A2 bar. Similarly, the third letter will not be in its right envelope, A3 bar, and this thing goes on, AN bar. That is, the nth letter will not be in its right envelope. I want to find out the total number of ways of doing such arrangement. Now, from here we can easily see, from the De Morgan's law, we can write this thing as A1 union A2 union A3 union so on AN whole complement. Correct? Whole complement. Now what is that? It is total number of ways where n letters are arranged in n envelopes. Correct? This is the total number of ways where n letters are arranged in n envelope minus the total number of ways where A1 union A2 union A3 goes on till union AN. What do you mean by that? What is this? This is at least one letter is in right envelope. What is A1 union A2 union AN? It means that at least one of these letters, A1, L1, L2, L3 and so on, they are placed in its right envelope. Now, what will be the total number of ways when n letters are arranged in n envelopes? But before that, let me just do one thing. Let me denote this thing by dn. Okay, this is dn actually represents the total number of derangement possible. So I'm writing it here. So your dn gives us, the first thing is total number of ways where n letters are arranged in n envelopes. So there are n letters and there are n self-addressed envelopes. The number of ways these n letters can be arranged or it can be placed in this n self-addressed envelope in factorial n different ways. Am I correct? There are n letters and there are n envelopes. One envelope can hold only one letter. So in how many different ways these n letters can be placed in these n envelopes? It will be factorial n different ways, right? Minus, from the inclusion and exclusion principle, we know that this can be written, n of A1 union A2 union A3 union till AN can be written as sigma n A1 excluded. This is included all the possibilities of taking one letter and then we are excluding two letters taken at a time. Then we are including 3 letters taken at a time, and so on. Is it clear? So the last one will be, you see the sign is plus minus. So let me just write -1 whole to the power n minus 1 into n of A1 intersection A2 intersection A3 intersection so on intersection AN. Okay. So this becomes what? Factorial n minus. Now sigma of n A1. What do you mean by that? It means n of A1 plus n of A2 plus n of A3 till n of AN. So the total number of ways of doing this, first you choose, there are n letters because you have to find out n A1, n A2, n A3 till n AN. So let me just choose first one letter from the available n letters. Let us say it is A1. And what does n A1 represents? It represents that the letter A1 will be it is placed in its right envelope. That is, it is placed in the envelope E1. Is it clear? So total number of ways that can be done. I mean one letter, first let us select one letter which can be done in NC1 different ways. And then that letter, whichever letter you have chosen out of that n letters, you are placing it in its right envelope, which can be done only in one way. And the rest letters left are n minus 1 and available envelopes are n minus 1. So these n minus 1 letters can be arranged in this n minus 1 envelopes in n minus 1 factorial different ways. Is it clear? Now let us consider the second one, which is n of A1 intersection A2. That is, out of this n letters, we are selecting first, we are selecting 2 letters. In how many different ways we can select 2 letters out of this n available letters? It is NC2. Now after getting these 2 letters, all I am doing is, I am placing those 2 letters in their right envelope, which can be done in only one way. And we are left with n minus 2 number of letters as well as n minus 2 number of envelopes. So they can arrange among themselves in this n minus 2 envelopes in n minus 2 factorial different ways. See the third one, we are having actually sigma n of A1 intersection A2 intersection A3. That is, we are choosing 3 letters out of the available n letters, which can be done in NC3 different ways. And these 3 letters are now placed in their right envelopes and which can be done only in one way. And the rest n minus 3 letters will be arranged in the available n minus 3 envelopes in n minus 3 factorial different ways. Clear? And this thing goes on. And when we come to the nth letter, we are now choosing n letters out of n letters which can be chosen in NCn different ways. And they are placed in their right envelopes and which can be done only in one way. All the n letters are placed in their right envelopes. That can be done only in one way. So it is one way. That's it. Now no letters are left, so no question of arranging any more letters. So that's it. So what will be our Dn? Let me just break this one. Minus NC1. NC1 is basically factorial n by factorial 1 into n minus 1 factorial into n minus 1 factorial. The next one is NC2, which is again factorial n divided by factorial 2, n minus 2 factorial into n minus 2 factorial. Again, the third one will give us factorial n divided by factorial 3, n minus 3 factorial into n minus 3 factorial. And this thing goes on again. So the last one will be minus 1 whole to the power n minus 1. NCn means factorial n divided by factorial 0 into factorial n. That's it. Now if I open the brackets and if I take n factorial common, we are having, if I take factorial n common, we are left with 1 minus, you see this one and this one will get cancelled. This one goes off, this one goes off. So ultimately we are having factorial n, and factorial n we have taken common, so we are left with 1 over factorial 1. And from the second one, factorial n is already taken common, so we are left with 1 by factorial 2. From the third one again we are left with 1 by factorial 3, and this thing goes on. And when we have opened the bracket, so this one will be minus 1 whole to the power n minus 1 into 1 over factorial n, right? Now, factorial n, 1 minus 1 by factorial 1 plus 1 by factorial 2 minus 1 by factorial 3. This thing goes on. Now, you see, minus 1 to the power n minus 1. Minus 1 to the power n minus 1 can be written as minus 1 whole to the power n into minus 1 to the power minus 1. And this thing actually gives us minus 1. So it will be minus 1 whole n. So this thing will become plus minus 1 whole n 1 by factorial n. Am I correct? So this is our derangement formula that we got. This is our derangement formula that we got. I hope it is clear to everyone. So, in how many different ways n objects be placed in n places in such a way that no objects are in the right position? And as I told you, this is your derangement problem. And the formula that we have derived from the principle of inclusion and exclusion is dn is factorial n into 1 minus 1 by factorial 1 plus 1 by factorial 2 minus 1 by factorial 3 till it goes on. The last term will be minus 1 whole to the power n into 1 by factorial n. I hope this is clear to everyone. This is the first method that we have used to find out the derangement problem. Now let us try to establish the same formula by using recurrence relation. Now the first question will come in our mind that, sir, what is recurrence relation? What is recurrence relation? What do you mean by recurrence relation? Actually, recurrence relation is an equation which represents a sequence based on some rule. Okay? It is based on some rule. It helps in finding the subsequent term dependent upon the preceding term. Is it clear? Depending upon the preceding term. Like if I say an is 3 times an minus 1. So to know the subsequent term an, which is dependent upon the preceding term an minus 1, or it's a combination of the preceding terms. This is what is called your recurrence relation. Now, how to use this recurrence relation to find out the number of derangement possible? There are n letters. Let me just draw it again. There are n letters like this. Letter 1, letter 2, letter 3, letter n. And there are n self-addressed envelope E1, E2, E3, En. Okay? Now let us denote Dn. What does Dn represents here? It represents that n objects, or in this case letters, are deranged in n self-addressed envelope. Okay? Self-addressed envelope. This is represented by Dn. Dn is what? N letters are deranged in n self-addressed envelope. Means no letter is going to its corresponding envelope. Okay? So now this Dn, I have to form an equation involving Dn and the combination of the previous terms. How to do that? Okay, so Dn represents what? N letters are deranged. Okay, this is equals to. Now, think about it. Let me say that you choose any of one letter out of this n letters. Any one letter. Let us choose L1. And this L1 letter which you have chosen, now you place it in any of the n-1 envelopes that we have. Why we are not considering n envelopes? Because your L1 cannot go to E1. That is envelope 1. So we are eliminating first envelope 1. And now we are left with n-1 envelope. You choose any one envelope to place this letter L1 in it. So we are left with n-1 envelopes. So L1 can be placed in any one of these n-1 envelopes, which can be done in n-1C1 different ways. And let us say we have chosen the envelope E2. That is, you are placing this L1 in E2. You are placing the letter L1 in E2. Clear? Now you see, we are having two possibilities of derangement. What are those? First is, let me put this letter L2 in E1. If we put L1 in E2 and L2 in E1, then we are left with n-2 letters and n-2 self-addressed envelope. Already L1 and L2, they are deranged. Now the n-2 letters, and we are having n-2 envelopes, as I said, they can be deranged. In how many different ways? n-2 letters can be deranged in how many different ways? Dn-2. Yes or no? What do you mean by Dn? Dn is the n letters are deranged. So what is Dn minus 2? It is n minus 2 letters are deranged. When L1 is placed in E2 and L2 is placed in E1, these two letters are already deranged. So we are left with n minus 2 letters which can be deranged in Dn minus 2 different ways. So that's exactly what I have written. This is the first option. And what is the second option? Let us assume that this L2 has not occupied the envelope E1. What I'm saying is this one, this letter, this L2 is not placed in E1. What I want to say is, now we are having, look it carefully, now we are having the letters, let me write it here, L2. What are the letters we are having? We are having L2, we are having L3, and so on, and we are having Ln letters, and the envelopes are E1, E3, E2 has already been occupied by L1, so I'm not writing it, En. Now in this case, what we have planned? We have planned that your L2 letter will not come in the envelope E1, because these are the two options you have. The moment I add these two options, you are going to get the total letters dearranged in how many different ways? Isn't it so? L1 and L2 are the two letters that we have chosen. Now, there are two options we are having. That is, suppose L1 is placed in E2, then your letter E2 have two options. Either it can come in the envelope E1 or it will not come in the envelope E1. That's it. And if you add these two cases, you are going to have the total derangement. Is it clear? Now, L2 will not come in E1. We are now having n minus 1 letters and n minus 1 self-addressed envelope. L2 is not going to come in E1. L3 is not going to come in E3, and so on. Ln will not come in En. So there are n minus 1 letters, so they can be deranged in Dn minus 1 different ways. Therefore, the total derangement will be d of n minus 1 plus d of n minus 2 into n minus 1 C1. So that implies your Dn is n minus 1 dn minus 2 plus dn minus 1. That's it. That is the recurrence relation for the derangement. Isn't it very fantastic way of solving derangement problem? That is why recurrence relation is so very popular. Okay, you see how short, in a shorter way we have done this problem, isn't it? Now the question comes, in this case, always remember, in recurrence relation, we always need some initial values. In this case, let us find out what is our D1. What is our D1? It means what? That there is one letter and there is one self-addressed envelope. In how many ways you can derange it? We are having one letter and one envelope. In how many different ways you can derange that? Obviously, one letter and one envelope, you cannot derange it. Therefore, D1 is basically 0. And what about D2? D2 means we are actually having two letters and two envelopes. Let us say L1 and L2 and E1 and E2. In how many different ways these two letters can be deranged in two self-addressed envelopes? There is only one way. Can you observe that? L1 can be placed in E2 and L2 can be placed in E1. That's it. No more options are left. So your D2 is nothing but 1. Is it clear? Only one possibility is there. Thus, this relation dn equals to n minus 1 into dn minus 1 plus dn minus 2 when d1 is 0 and d2 is 1. And this relation will hold true when n is greater than or equals to 3. Is it clear? Because the initial value we have already considered d1 and d2. So this relation will hold true when it starts from 3 onwards. Is it clear? So let me just shift this one here. So we are actually got this one as a formula for the recurrence relation for the number of derangement. Now the question comes, sir, whatever we have done here, we got this result, right? Your dn is, let me just copy this one. Just 1 second. So that I can take this thing in that page. So let me take this thing in this page. So this is the formula that we got, right? I'm writing it here. I'm pasting it here. Okay. Let it be like that. Okay. So we got this. Now a general question can come, sir, can you find out this relation from the derangement relation that we got? Well, let's try this one. We are having dn as n minus 1 into dn minus 2 plus dn minus 1. So let me do one thing. Dn equals to n minus 1 dn minus 2 plus n dn minus 1 minus dn minus 1. So let me take this thing in the left hand side. So we are having dn minus n dn minus 1 is basically n minus 1 dn minus 2 minus dn minus 1. Am I correct? Okay. So let me do one thing. Let me take a minus common. So we are left with dn minus 1 minus n minus 1 dn minus 2. Okay. Now, can you observe one thing? This one and this one, they are same. Why? Because here there is dn minus n dn minus 1, which is written in this way. Now, you see this one. This is what? Again, this is the same thing. dn minus 1 minus n minus 1 n minus 2. That is, in place of n, I have simply replaced by n minus 1. So this can be written like what? Again, minus 1 will come out. It will be n minus 2, n minus 2, n minus 3. And this thing will goes on. Tell me yes or no. This thing will goes on. Again, you see, this one is same thing. So again, in place of n, I'm writing n minus 2. We are getting this. So what we are actually going to have, again, a minus 1 will come out. And this can be written as d of n minus 3 minus n minus 3 dn minus 4. Right? And this thing will go on. So one term will come at the end where you will get, I'm writing it here. At last you are going to have, if we proceed in this way, minus 1 whole to the power, let us say n minus 2. So in that case, what will happen? If this is n minus 2, it will be d of n minus n minus 2 minus n minus 2. This one will become plus then. And in this case, it will be d of n minus n plus 2 minus 1. So what we are getting? dn minus n dn minus 1 is minus 1 whole to the power n minus 2. This is your d2 minus 2 times d1. Am I correct? Now we already got that d1 is 0 and d2 is 1. So if I replace, we are going to have dn minus n dn minus 1 is basically minus 1 whole to the power n minus 2. This can be written as minus 1 to the power n into minus 1 to the power square. And d2 is 1 and d1 is 0. So we are actually having minus 1 to the power n. Is it clear? So we got dn minus n dn minus 1 is minus 1 whole to the power n. Let me go for the next page. So what we got? dn minus n dn minus 1 is minus 1 whole to the power n. Now I am dividing both sides by factorial n. So what we are getting? dn by factorial n minus n dn minus 1 by factorial n minus 1 whole to the power n by factorial n. So we are having dn over n factorial minus dn minus 1 over n minus 1 factorial minus 1 whole to the power n by factorial n. Now let me just put n equals to 3, 4, 5 and so on till n. So what we are getting? d3 over factorial 3 minus d2 over factorial 2 is minus 1 whole square divided by factorial 3. Am I correct? I'm sorry, this is whole cube, right? Whole cube by factorial 3. Because in place of n, we are putting 3. So now, if I put 4, we are going to have d4 over factorial 4, d3 over factorial 3, minus 1 whole 4, divided by factorial 4. Again, in this case, if I put 5, I hope it is clear to everyone. And this thing will go on. So at last what you are putting? You are putting n. So it is dn over factorial n minus dn minus 1 by factorial n minus 1 is minus 1 whole n by factorial n. Now, if I add the corresponding sides, look at very carefully. If I add the corresponding sides, this will go off, this will go off, this will go off. So ultimately this will go off. So we will be left with dn over factorial n minus d2 over factorial 2 equals to, this is minus 1 by factorial 3 plus 1 by factorial 4 minus 1 by factorial 5 plus this thing goes on plus minus 1 whole to the power n divided by factorial n, right? And d2, as we all know that your d2 is 1. So we will write dn over factorial n is 1 over factorial 2 minus 1 over factorial 3. This thing goes on till the last term. Right? So what is your dn? It is factorial n multiplied with this whole thing, but just to establish that formula, I'm simply adding 1 and subtracting 1 to maintain the parity of the sequence. 1 by 4 and this thing goes on. So the last term will be this one, right? You see, exactly the same thing that we got, when we have proved this by using your principle of inclusion and exclusion. We got the same result. Can you see that? This exactly the same result, we got it here. So what we have learned in this video is that what is derangement and how we establish the formula by using two methods. One is principle of inclusion and exclusion Another one is the recurrence method. Hope you have enjoyed this video. Please do subscribe and press the bell icon to get this kind of video in the coming days. We will meet very soon in my next video. Till then, goodbye and take a very good care of yourself.